Hello, welcome to the 2.4 notes. Today we are talking about differentiability and continuity, and we're connecting the two. So, a fun fact is there are places on a function where the derivative doesn't exist. In order for the derivative to exist, the left-hand derivative has to equal the right-hand derivative. And that makes sense because it makes sense that there's places where a derivative doesn't exist, because a derivative is essentially just the limit. It's not essentially, it is the limit of the average rate of change. And so we know from the first unit that limits don't exist places. And so if limits don't exist places, that means that it's possible for the derivative not to exist places. The problems that I've given you, I have not given you a problem yet where the derivative doesn't exist. So we haven't had to think about this hard yet, but now we're going to have to start thinking about it. And so if the condition isn't met, this left and the right-hand limit isn't met, there's going to be three things that you might see on the graph. And so the first one is a vertical tangent at the point that it's asking you to find the derivative. You could see a sharp point, and you'll see more what that means in a second. Sharp, put that in quotations. And then it's going to be not continuous at that point that you're asked to find the derivative. So one of those three things will happen. If any of them happen, that means that the function's doesn't have a derivative there. And so if you see one of these things on the graph, or you prove discontinuity, so if those two things, if you see something on the graph like a tangent or a sharp point, or you can prove discontinuity, you can automatically assume the function isn't differentiable there. And so first, let's look at the example of a vertical tangent. So if you look at this function right here, this is the cubed root of x, and at x equals 0, the derivative does not exist. And that is because the tangent line here is just vertical. If someone was to ask you to draw the tangent line at x equals 0, it would just be a vertical tangent, and there's no slope to a vertical tangent. There's a change in y, right? There's a change in y. Like if you went from 1 to 2, there'd be a change in 1 for the change in y, but there'd be no change in x, so you'd have 1 over 0, and that does not exist. And so at x equals 0, the derivative does not exist because there's a vertical tangent. And the essential reason why is because the derivative is the slope of the tangent. There is no slope of that tangent line. Same thing over on this one. There's a vertical tangent here. I think this is at x equals 2. So x equals 2, derivative does not exist. So if you're given the graph and you see this, like, you don't have to necessarily prove anything crazy. You can just say the derivative doesn't exist because there's a vertical tangent there. So our next examples are graphically is if there is a sharp point. So if you look here at this graph right here, there's a sharp point at x equals 0. And so the derivative doesn't exist there. And if you want to think about it with what we know about derivatives, is that what we've learned about derivatives so far is it is the limit of the average rate of change. Well, if you think about what the limit of the average rate of change is here, so what's the average rate of change as we get closer and closer and closer to 0? Well, that's going to be a negative number if you think about it. And then it's all of a sudden just going to get to this point. This one's also going to be a negative number, right? They're getting really, really close here, but there's not really any pattern that's happening at that point. And so it kind of just breaks there versus like when we've been doing quadratics, it's rounded. So you can kind of slowly get closer there, but that just doesn't happen here because there's this sharp point. So the left and the right hand limit wouldn't equal each other. And then here again, this is at x equals -3, the derivative doesn't exist because of a sharp point. So anytime you see an absolute value function, the point, like the point of it, that the derivative doesn't exist. But like if someone were asked to find the derivative at -5 of this absolute value, it would exist because you can find the average rate of change from the left and the right hand and they'll equal each other. But the tip of an absolute value function, the derivative is never going to exist there. So keep that in mind. The last one is the derivative does not exist at a point because it's not continuous. So the derivative doesn't exist at x equals 1. There's a jump discontinuity. Continuity doesn't exist over here at x equals 2 because derivative does not exist because there is a removable discontinuity. So that is a bunch of graphical representations of how you can tell when a derivative exists or doesn't exist. But we're going to explore some continuity and differentiability with algebra. So obviously every time we move into the algebra, things get a little bit more complicated, but we're really basically just using the equations that we're given to figure out what's happening on the graph. And so our key theorem, the most important thing we see here, and sorry, this should say then, is if f is differentiable, at x equals a, so at some point, then f is continuous at x equals a. So if you don't know what the word differentiable means, we haven't directly used it, but you might be able to assume all that word means is it means you can take the derivative. So if you can take the derivative, let's say at x equals 3, then what that automatically implies is that at x equals 3, the function is continuous. And so in that one, a couple weeks ago, we looked at the intermediate value theorem problem, and I told you, like, oh, it says it's differentiable, so that means it's continuous, and we didn't have that knowledge yet of what that meant, but this is what this means now. So if you can take the derivative, it's also continuous. And so some important ideas that come from that, and this is just like logically, if you were to think about this, is if f is not continuous at a, then there's not a derivative at x equals a, and we've kind of already discussed that above. But if f is continuous at a, that doesn't automatically mean there's a derivative. That just means that there could be a derivative. And so what I want you to know is, like, this doesn't work both ways. Like, just because it's differentiable, if it's differentiable, it means it's continuous, but it doesn't work the opposite. So just because it's continuous doesn't mean it's differentiable. It's kind of like the square rectangle idea. Like, a square is automatically a rectangle is not automatically a square. So if f is continuous at a, then there may be a derivative there, but it's not a guarantee. And so the reason this is so important is because of things like the intermediate value theorem, or later we're going to talk about the extreme value theorem. There's also something called the mean value theorem. And so all of these theorems, you need to know whether something's continuous and differentiable for them to work. And so that's why the connection between these two things is so important. So example 1 is we're going to be asked, is the function differentiable and continuous at x equals 3? So the thing about differentiability is, like, it's kind of like continuity. Like, if you're working with x squared or 4x plus 3 or any polynomial, right, it's obvious that it's continuous because the domain of those functions is negative infinity and infinity. And so differentiability works the same way. Like, those are very basic functions. There's nothing too crazy about them. If their domain is negative infinity and infinity, they're going to be differentiable. But now we're going to look at a piecewise function. And anytime we look at piecewise functions, we have to be more wary because it splits into two pieces. And so the first thing we're going to, if the function's continuous and differentiable. So the first thing that we're going to check is continuity. And to check continuity, we got to go through our 3 steps. So if you notice, nothing in calculus really goes away. And so if there's things that you're still struggling with in last unit, don't ignore it because it will be back. So continuity, I'm first going to check that the point exists. So x is greater than or equal to is the one with the point. So I'm going to do f of 3 equals 6 times 3 minus 9, 18 minus 9 equals 9. So the f of 3 exists. Now I'm going to check my limits. My limit as x approaches 3 from the left of f of x is going to be 3 squared, which is 9. And then I already figured out what the right one is because I used it to find the point. And so that's going to be 9. So the limit exists because because x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right. And then my last step is to say that f of 3 equals the limit as x approaches 3. So f of x is continuous. So we know that f of x is continuous now. And because we know that it's continuous, that means it may be differentiable. Okay, but we don't know that for a fact, so this is how we're going to check differentiability. And really, just a reminder, you don't need to do this for every function you're given, but things like piecewise functions is a time that you really do need to check differentiability. If it's a basic function, you don't need to check whether left hand and right hand limit equals each other because you just know that. But the way that you check differentiability is you just do the limit as x approaches, in this case, a is 3, because that's where we're trying to check if it's continuous. As x approaches 3, we're going to use this notation, f of x minus f of 3 over x minus 3. Okay, And so because we're finding x as it approaches 3 from the left, we're going to use the x squared function to answer all of these questions about the left-hand limit, because that is where the limit, that's where that's the function that we would use to find the limit as we approach 3, because it's the left-hand values. So I would do x squared minus, and then I'd plug in 3 for x squared, 3 squared all over x minus 3. And that gives us the limit as x approaches 3 of x squared minus 9. With this function, like with this method of finding the derivative, the second definition, you just really have to be comfortable with the difference of squares. So x squared minus 9, if I were to factor that, I get x minus 3 times x plus 3. These cancel out. And now I have this, and I can just go ahead and plug in 3 there. So I get 3 plus 3 equals 6. So the left-hand derivative is 6. Now we need to see if the right-hand derivative is 6. So that was kind of like step 1. I'm just going to do that. Step 2 is now we need to check the right-hand derivative. It's basically the same process, but we're going to use this function now, because this is where the x values are greater than 3. So I'm going to use 6x minus 9 to check that one. So I'll have, again, f of x minus f of 3, same definition, just using the different part of the function. So I'll have 6x minus 9 minus, if I plug 3 in there, 6 times 3 is 18. 18 minus 9 is 9 all over x minus 3, which will give me, you can make sure I did that right. Yeah, I did. Okay. That gives me the limit as x approaches 3 from the right of 6x minus 9 over x minus 3, which equals the limit as x approaches 3 from the right of 6x minus 18 over x minus 3. So I can't plug in 3 yet because I haven't canceled out a factor. But if you notice, the greatest common factor of 6x and 18 is 3. So I can pull that out and I'll get, the greatest common factor between 6 and 18 is 6. So I'll get x minus 3 all over x minus 3. These cancel out and I'll get the limit as x approaches 3 of 6, and that just equals 6 because all the x values canceled out. So if you look there, the left-hand derivative equals the right-hand derivative, so we know that is also differentiable because, and you do need to give me a little explanation. I know that you showed your work, but you got to kind of do a conclusion statement, because we can just write left-hand derivative at 3 equals right-hand derivative. Or you could write that notation. I don't know which one's faster. And so that's the answer to this one. It is differentiable and it's continuous. And I'm going to show you the graph of this so I know, right? If you look here, they connect there, they're differentiable there. So let's go on to a next example. Next example is another piecewise function. Is the function continuous and differentiable at x equals 1. So same thing, and this is really just like process. And you can go through this quicker if you know how to go through this quicker. But I'm first just going to check if it's continuous first. You also could check if it's differentiable first. I haven't decided which one's better. Okay, number 1. F of 1. Checking that. So I'm going to do 7, 1 squared minus 12. That's going to equal negative 5. So f of 1 exists. 2. The limit as x approaches 1 from the left is going to be 1 squared minus 4, which equals negative 3. Wait. What am I doing? Oh. Okay, sorry. Yeah. That equals negative 3. The limit as x approaches 1 from the right is 7 times 1 squared minus 12, and that equals negative 5. So the limit does not exist because the limit as x approaches from the left does not equal the limit as x approaches 1 from the right. So what that means, because the limit doesn't exist, that means f of x, someone writes, so f of x is not continuous. And if f of x is not continuous, so f of x is not continuous and therefore is not differentiable. So if a function's not continuous, it's not differentiable either. And so sometimes these problems are kind of easy because if you realize it's not continuous, then you can be done. So f of x is not continuous and therefore it is not differentiable. So you're done with this one, not as bad. and this is what the graph looks like. So, sorry, it gets kind of cut off, but you can tell right there that there's a little bit of a jump discontinuity between those two different functions. Okay, we have one more. Okay, our last example is example 3 is the function differentiable in continuous at x equals 0. So this is an absolute value function, and one thing that you might not really know about absolute value function is you can actually represent it using a piecewise function. That's not really necessary if we're just trying to find the continuity of the function, but it is going to be necessary if we're trying to find whether it's differentiable or not. So x, the square root of x equals, and I have the graph down here if you guys want to look at it, but if you really think about this graph, spoiler, we know that it's not differentiable because there's a sharp point, but I'm going to show you like how you would know that from the equation. But basically it's split into two pieces. It's split into this piece right here, and that's just the function x, and then it's split into two pieces right here, and then if you were to find the equation of that line right there, that'd be negative x. And so if I go back up here, I know that the square root of, or the absolute value of x is essentially equal to negative x when x is less than or equal to 0. It doesn't really matter which one has the equal to for this. And then it's x when the x values are greater than 0. And so I'm going to by finding continuity. And so f of x just equals, it really didn't matter which one I used, but negative 0. So f of 0 exists. Step 2, the limit as x approaches from the left of 0, well, negative 0 is just 0. And then the limit as x approaches from the right of 0, positive x is just 0. And so the limit exists. And then we already know this to be true, but f of 0 equals the limit as x approaches 0 of f of x, which equals 0. Now, though, things are going to get different when we check differentiability. So we obviously know that the answer is going to be no to this, but let's assume that we didn't know that. Then the limit as, we're going to do the limit as x approaches 0 from the left of f of x minus f of 0 all over x minus 0. So we're going to have the limit as x approaches 0 from the left. We're using this one right here first because that's where the x values are less than 0. We'll have negative x minus 0 because f of 0 is 0. And then I can simplify here down on the denominator because x minus 0 is just x. And then on my numerator, I'll have, once I simplify that, I'll have the limit as x approaches 0 from the left of negative x over positive x, and that equals the limit as x approaches 0 of negative 1. If I plug in 0 to that, I just get negative 1. So the left-hand limit is negative 1. Now I need to check the right-hand limit, or the left-hand derivative is negative 1. Now I need to try the right-hand derivative. This time we use this one right here because this is where the x values are greater than 0, and we'll get x, sorry, I have to write this all out. We will get x minus 0 all over x, and that simplifies to x over x, which simplifies to 1. And so the left-hand limit, or the left-hand derivative and the right-hand derivative don't equal each other, so it's not differentiable. And that is it with the 2.4 notes. Thanks for watching.